I'd like to welcome one of the organizers, Shay Moran, who is now at Technion, and he was part of many breakthrough results recently about this active learning and decisions trees about the case sum problem and other problems. And luckily, he always had a very strong kind of geometric interest and also he has some geometric papers that are very exciting to me. So I am excited about his talk and even took a notebook because I am going to take notes of his lecture. So thank you very much for preaching to us.
Okay, thank you, Janos. That's embarrassing. But sure, I'll do my best. I hope something will be written eventually in the end of the talk in your notebook. So I will talk about, what more in the most general, the most general topic I will talk is the expressiveness of comparisons, and as we will see, this will also lead to this case sum related question. So first of all, like a little bit also, I mean, to connect it to the topic of this workshop is that so by now we see in many cases in machine learning that machine learning settings, they give rise to combinatorial parameters, and two famous examples are back learning in the Lewis dimension and online learning in the Littleson dimension, and it's useful in both contexts. Today I will present to you another manifestation of this link in interactive learning and the inference dimension, and which I don't know if I'll have time to show you how we use it, but luckily Shachar Lovet is talking after me and he will present a follow-up work. So, but again, like also in this context, we just studied some esoteric model of learning that only we cared about. And we try to really understand the complexity, how to combinatorially capture the complexity there, and then as a corollary, we were able to answer this question. And I'm pretty sure that if we were to study this open problem directly, then we wouldn't have solved it. So it was only thanks to this learning theoretic perspective that allowed us to develop this combinatorial parameter. That was the crux of the solution. Okay, so I will speak first about this paper, and maybe only about this paper depending on the time, and it is with Daniel Kane, Shachar Lovet, and Jiapeng Zhang. At the time, they were all in San Diego. I think today Jiapeng is in University of South California, if I'm not mistaken. He became a professor there. Okay, so before we dive into the fun, the mathematics, let me talk a little bit about the motivation. So what is active learning? Okay, so in passive and super classical supervised learning, we're given labeled examples, and we need to learn how to label unseen examples. Okay, so the examples, for example, the examples may be medical files and the labels may be diagnosis of them. In active learning, we're given many unlabeled examples, and we can query the labels of some of them, hopefully as few as possible, and we still wish to be able to predict as well as if all labels are given. So for instance, you can think about that the unlabeled data is again medical files, and in order to get the labels, the diagnosis, you need to have the files inspected by a doctor, by some expert. So when is this possible? Okay, so let's consider a very, very simple toy example to just get used to this model. So imagine we have unlabeled points x1 up to xn on the real line. So this is our input. And we also know that there is some unknown threshold, T. We don't know what T is, but we know that above this threshold, every point above this threshold is labeled positively, and every point below this threshold is labeled negatively. And the question is, how many labels must we query in order to identify all labels? So the solution is, of course, binary search. So let's see an illustration of it. So we begin with the middle point, and then we see that the label is plus. And then immediately we can infer that everything to the right of this middle point must also be plus, because it's a threshold. We know that it's an unknown threshold. Then we query the middle of the remaining unknown interval. Again, we see it's minus, and then everything to the left of it must be minus. And this way, we proceed log n iterations, and we infer all of the labels. Okay, so we see that with just log n label queries, we are able to infer all the labels given by some unknown threshold. Now, the unfortunate fact is that this nice kind of behavior that we see in the real line can't be extended, not even in 2 dimensions. So, okay, so what is the 2-dimensional variant of this problem? So now instead of thresholds, we have half planes. Okay, so again, it's the same setting exactly. We have n, x1 up to xn are just n unlabeled points in R2 in the plane. There is some unknown line that separates the plane to 2 half planes. One of them is positive and one of them is negative. And our goal is to query as few points, as few data points from the x1 up to xn as possible, and to infer the labels of all endpoints. Okay? So as I promised you, unfortunately, this is impossible in general. So if you assume that the n input points are in convex position, so for example, on a circle like this, then what does convex position mean? It means that for every point can be separated from the rest by some line, by some, and therefore, if you can imagine an adversarial argument that always labels the point red, and there will always, unless you query all points by 1, there will always be at least 2 possible extensions that are consistent with the data. So there will be some uncertainty. Okay, so this is not a formal proof why it's impossible, but it's just to give you an idea that that even if you label n over 2 points or omega of n points, then you still don't have enough information to deduce the rest. To make it formal, you want to make you pick a point, you pick a line separating a single point in random, and you argue that if you query less than n over 2 points, then you cannot, and the algorithm cannot infer the rest. Okay, so you really need to query essentially all the points here. And the question is how, like, what to do next, like how to, like, we wish, to study interactive learning models in which you can solve such simple basic problems such as half planes. And then, and this is like a scientific question, what model should one consider, which is interesting and natural, and so what we do is what is becoming also very useful in practice, is to allow additional interaction with the labeler, with the expert. And now you can ask yourself which additional queries to ask, and of course this is problem dependent. But one type of queries which are useful in practice are what they call relative queries. So you can imagine, like in a restaurant recommendation system, that there is a label query. So you have on your smartphone some restaurant recommendation app, and to whichever restaurant you go to, it will ask you, did you like this restaurant or not? So this is a label query, like we studied before. But then you can imagine that it can also ask you, okay, you told me that you like both Falafel Zohar, which is a falafel next to the Technion, and McDonald's. Which one of these two restaurants did you like more? Okay, you can also imagine this kind of questions. Other type of relative queries that are useful in practice are like these triplet queries. And you can ask about a triplet of points, a triplet of data points, which two are more alike. So this is basically what inspired our work. And let me now present the formal setting. So we assume that the target labeling function is of the following form. There is some underlying class F of real valued functions, and we will just think about half-spaces. So F is just affine functions, but F can be more generally polynomials or whatever you want, neural nets, you name it. And the labeling function is just the sign of G, where G is in F. So H is a family of Boolean functions, of plus minus one functions that are obtained by taking the sign over a family of real valued functions. And now we consider two types of queries. So there is the good old label query, where we ask, is the sign of G, of the target function, on xi is positive or negative? So this is just what we had before. But we also allow now this comparison query. Is G of xi at least G of xj for a pair of input points, xi and xj? So, for example, if G is an affine function, notice, and let's say xi and xj are two positive points, so they are on the positive side of the half space. Half space is considered of the hyperplane defined by G. Then G of xi is greater than or equal to G of xj if and only if xi is further away from the hyperplane than xj. Okay. So the comparison query, you can think about it like, okay, you told me G says that it's positive or it's negative, but is it more positive? Do you like this restaurant more than the other restaurant? How positive, how much more positive is this? But let me stress that these are just, all of these queries are binary answers. So we don't get any real values from these queries, are just yes, no queries, basically. Okay, so this is the model. Okay, so now let's go back to the planar problem. Okay, so let's see now that I will give you an algorithm that will show you that that we can actually retain back this logarithmic advantage. Okay, so the crucial point I want you to remember is that is the combinatorial semantic of a comparison query. So a comparison query basically compare the distance of the 2 points from the separating line. Okay? Okay, so this is geometrically the semantic of such a comparison query. Okay, so let's see how it works. So this is how our input looks like. We have n unlabeled points. They're black, they're all black in the plane. There is this unknown line that we don't know, but I just draw it for convenience. And now the algorithm proceeds as follows. So in each iteration, we sample 10 points from the endpoints, from the domain, from the input. We label them. Okay, so we find which of them are positive and which of them are negative. Then we use comparisons to detect the red point, which is closest to the separating line, and the blue point, which is closest to the separating line. Okay, so this is just like finding a minimum in an array. So this costs us another 10 queries, less even. Okay, and then what I want you to notice is that if we consider these two cones that So the red cone is defined by taking the closest point to the green separating line and the two neighbors on the boundary of the convex hull of the red points, and then you shoot, you generate this angle. And the observation is that within these two angles, within the red angle and the blue angle, the labels must be positive or negative, respectively. Okay, so what we can do now is we can just label all points that are in the union of these two angles. And we know that for sure we have labeled correctly. So we can now remove them. And we repeat the process on the remaining unlabeled points. And the crucial lemma that we will discuss in a little bit more detail later, when I define the combinatorial dimension, is that in each iteration, we infer, so each iteration is a random, there is a randomized component here, right? We sample 10 points from the remaining unlabeled points. So in expectation over this sampling, we infer the labels of half of the remaining points. So in each iteration, half of the labels are being inferred. And in each iteration, we use 20 queries, right? 10 label queries plus less than 10 even comparison queries. So the expected number of queries is at most 20 log n. Okay, does it make sense? Good. Okay, great. So let me now quickly state the main results. So for Halfspaces. So first of all, let me begin with bad news, but also an open question. So the bad news are that in R3, there exists for every natural number n, a rather exotic set of n points in R3, such that one can prove that you need at least order n label and comparison queries for revealing all labels. Okay, so comparison queries work for the plane, but they fail to work for the three-dimensional space. And one open problem, or let's call it a meta-open problem, which one can explore in this context is that, so notice that on the real line, we did this binary search, right? And we did it with log n queries. So we only need labeled queries, which involve a single point. But then when we went to the plane, these labeled queries will not suffice because of this convex position. But once we introduced the comparison queries, then all of a sudden it was okay, and we were again able to retain this logarithmic behavior. And comparison queries, they involve just a pair of data points. So a single data point label query, enough for the real line. A pair of data points, a query involving a pair of data points is enough for the plane. Is it true that in general, one can define a natural query which maybe involves d data points in RD, such that there is an efficient querying scheme that reveals all label very, very fast, much faster than. So is it true that there is like a correspondence between the dimension and the locality of the queries? Okay, I hope this makes some sense. Okay, but as I said, going back to comparison queries, so such point sets are exotic in R3, and we can do much, much better when the input is relatively well behaved. So it doesn't even have to be so well behaved, but only not too crazy. So for example, if it's on a grid, I will show you soon, and also in the case of large margin, which Shachar will, I think, discuss further in his talk. Yeah, so the bit complexity, the grid, so assume now that each point xi, so each of the n points has only integral values of bounded size, at most b different sizes. So between 0 and b minus 1. Then all the labels can be revealed using d log b log n queries. Okay, so And just a comment, notice that this constant in front of the log n, so again, we retain the log n dependence, and the constant in front of log n is d log b, which is exactly the description length of each point in bits. And now here is a comment which is related to the K-sum problem, or to subset sum, if you will. So if you take, imagine that the n points are all the points in this cube, this cube, all possible integers with coefficients between 0 and b minus 1, all possible integral vectors. So there are b to the d such points, such vectors, and you can infer all of them using just d squared log square b queries, which is much smaller than the number of points you have there. And this is basically the starting, the crucial observation that we do for the subset sum, means that you just b is 2 there. And the second kind of upper bounds we know to get is when you assume that there is a large margin. So margin is basically the formal definition is that whenever you're given such a labeled point set, right, that is labeled by a hyperplane, then the margin of this labeled point set is the ratio between the diameter of the point set and the distance between the positive and negative convex hulls. So if the margin is large, let's assume the diameter is 1. The margin is large if and only if the point sets are well separated. Okay? So what we can show is also that if you assume margin gamma, then all n labels can be revealed using d log 1 over gamma log n queries. And maybe one comment here, one caveat of our algorithm here is that it has to know the margin. And in learning theory, usually it's not a good thing. You want adaptive algorithms that not necessarily know the margin, but so this is one caveat. And yes, let me just know that similar dependence on margin appear in this heavy-duty LP solvers. And also let me know that it is impossible. So usually in machine learning, statistical learning, once you introduce margin, you usually want to avoid the dependence on the dimension. And it is impossible in this context. So we can find, if we allow very large dimension, then we can find point sets with a constant margin in which you require basically all queries in order to infer. Okay, so now let me pass to maybe the main technical contribution of this work, which is the inference dimension, which, as I told you, as I promised, it is a combinatorial dimension, which characterizes the query complexity in this model. And then maybe the conceptual contribution of this combinatorial dimension is that it reduces this algorithmic kind of question of finding an algorithm that queries the points, and it's like a very algorithmic question, to just bounding a combinatorial quantity. So you can forget about algorithms and you can just focus on computing a combinatorial quantity, and once you compute it, you basically solve the algorithmic question. And yes, and let me also mention that this inference dimension quantity extends to any type of local additional queries. So the triplet query that I mentioned before, and I think maybe in Shahar's talk, maybe he will mention applications of the inference dimension to more than just comparison queries. Okay, so let's define the inference dimension and see a couple of examples to internalize the definition. So we call that the object we're trying to learn, so that we know that is this class H, right? We know that the target function belongs to a class H, which is given in this form. So the inference dimension of this class H is the minimal number k with the following property. Every labeled set of size k must contain one point whose label can be inferred from asking the queries on the remaining k-1 points. Right, so in every set of k points, there exists a point. I don't ask you to find it efficiently or anything, but God knows a point, such that if you remove this point and then you ask all queries on the remaining k-1 points, and then you bring this point back without its label, then you can infer the label of this point from the information you had. Let's consider a couple of examples. So I claim that the inference dimension of thresholds over the real line is 3. Okay? So for the upper bound, what do I need to show you? I need to show you that whenever you're giving me 3 points, a labeled point, 3 labeled points, then there exists some point, one of the 3 points whose label can be inferred from the queries on the other 2. Okay, so there are 2 cases. Either the 3 points have the same label, it is plus, 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 then the middle point can be inferred, right? If I forget that the label of the middle point is positive, and then I ask myself, what can it be? Then it must be positive, right? Because if it were negative, then we would have 2 sign changes, plus, minus, plus. And 2 sign changes are impossible for thresholds, right? And similarly with minus, minus, minus. So this is case 1. 3 points have the same label. If they have different labels, then one of the endpoints can be inferred, right? If, for example, I have plus, plus, minus, and I forget the leftmost plus, and then I ask myself, what can the label be? Then it cannot be minus for the same reason as before. If it were minus, then we would have 2 sign changes, which is impossible. So it must be a plus, right? So I just argued why in every set of size 3, every labeled set of size 3 on the real line, there is 1 point that can be inferred, assuming the labeling function is a threshold, has at most 1 sign change. Of course, I need to also prove a lower bound, but this is not so exciting. And notice that here, by the way, we only use label queries to argue that the inference dimension is 3. We did not use any comparison queries. And this is related to the fact that on the real line, only label queries are enough. Okay, let's now consider the example of half planes. So again, I want to prove to you that the inference dimension of half planes is bounded. I will show you that it is at most 7. And in fact, it is 5, but you can consider it as an exercise. And I want you to notice how the proof, the reasoning that I will give you now, really resembles the algorithm that we have seen previously. So, okay, so I need to show you that whenever you give me 7 points, there is 1 point whose label can be inferred. Let's do that. So you give me 7 points. So there must be 4 points with the same label, right? We have 2 labels, we have 7 points, we have the pigeonhole principle, we have 4 points with the same label. And now, again, consider the point, so consider the cone. So let take from these 4 red points, take the point which is nearest to the separating line and produce the same angle we have produced before. And to define this angle, you only need 3 points. You need the apex and you need the 2 neighbors on the convex, on the boundary of the convex hull. And the remaining point, its label can be inferred. Okay? And notice that, you know, so what did we need in order to infer it? We only needed to know the labels of the 3 points, and we needed to know which one is closest to the line, to the separating line. And all of this information is implied by the label and comparison queries on these red points, on the 3 red points. Okay, so here I argue that the inference dimension is at most 7. And that's it. And then we give this general upper and lower bounds that, and I think the lower bound, by the way, can probably be strengthened. But the upper bound, anyways, tells you that whenever you have a labeled set of size n, there is an algorithm that uses just order of k log k times log n comparison and label queries. And the lower bound tells you that if the inference dimension is at least k, then you need at least omega k queries. And yes, okay, so this is basically the combinatorial parameter, this inference dimension. And I guess I don't have time to discuss this, right? How are we time-wise? How much time do I have?
You still have, let me see, 8 minutes.
8 minutes. So let me start, and then Shachar will continue, because so hopefully I will help Shachar.
You have 8 minutes together with the questions, but we can leave the questions after Shachar. So it's up to you.
Sounds like an excellent idea. So let me start. And please let me know like in 5 minutes or something if I forget. Thanks. Okay, so the second part of this talk, I want you to show how to use this theory we developed in interactive learning to solve this question about three-sum. So what is the three-sum problem? So we get as input, we have n numbers, x1 up to xn, and we have to decide whether there exists a triplet of indices that sum such that xi plus xj plus xk are equal to 0. This is like a problem from a basic class on algorithms. So by traversing over all triplets, you can do it in n cube time. And there are more clever algorithms. So there is one which uses sorting, which does it in n squared time. And the three-sum hardness conjecture says that n squared is essentially the best you can do. So any algorithm requires at least n squared time. And the reason the reason this conjecture arises is not because this problem is so not for the basic courses in undergrad. It's rather because this problem is a bottleneck in many other problems, especially with a geometric flavor, right? So if you can find a better algorithm for three-sum, then immediately you improve the state of the art for a bunch of other problems with the geometric flavor. And I don't want to get into it, to waste time on this. Now, one computational model which attracted a lot of attention in the context of this problem is the linear decision tree model. And okay, so people basically try to find explanations. Why is it hard to improve the n squared time algorithm? So there is a very simple n squared algorithm, and it is very hard to improve. And then they observed that the n squared algorithms, the way it accesses the data is very simple. It's basically only by comparisons. And then they said, okay, maybe like in sorting, we can convince ourselves that merge sort is optimal by showing that any comparison-based algorithm must use at least n log n comparisons. So we consider this ternary decision tree model. So you get the input, which you want to determine whether there is a three-sum there. There is a triplet that sums to 0. And the only access you're allowed to the input is basically to take a linear combination of the input and to ask what is the sign of this linear combination. Okay, so these are like generalized comparisons, if you will, right? Comparisons is just xi minus xj. It's a very simple linear combination. This is a little bit more general. So this is how the beginning of a linear decision tree can look like. And so of course we want to ask, like, in this model, how many generalized comparison queries are required to solve this problem? And yeah, so there has been a lot of work on this, and the best bound before our bound was n to the 1.5, which was already a breakthrough because it doesn't need this. It is below n squared, right? The conjecture was that it should be something like n squared. And what we prove is that you can do it in n log square n queries. And furthermore, you don't really need very crazy linear combinations. You only need these label queries. You ask whether xi plus xj plus xk is larger than 0, or comparison queries. You pick two distinct triplets and you ask which one has larger sum. Only these two type of queries are already suffice to determine this problem using n log n queries, basically, O tilde of n queries. Now, the last thing I want to show you before Shachar takes over is what does it have to do with the previous active learning problem? Okay, so this is so let's see this, right? So remember so now I will show you how to think about this three-sum problem as an active learning problem. So in the three-sum problem, we have this input array x1 up to xn. Think about it as a normal to a hyperplane that passes through the origin, right? So you have all the points that have a positive inner product with it, all the points that have a 0 inner product with it, and all the points that have negative inner product with it. There's two open Halfspaces and the hyperplane. Okay, so this is the target, the input array defines the target Halfspace. Now the unlabeled input points are just all points on the Boolean cube with Hamming weight 3. Okay? So we have n choose 3 points, n choose 3 unlabeled points. So the size of the data set is n choose 3. And notice that if we were able to find the inner product, the sign of the inner product between x and p for every of these points p, for each of these points p, for each of these points p, then not only do we know whether there is a triplet that sums to 0, we actually know the sign of the sum of each and every triplet. Right? So if we are able to determine for every of these n choose 3 points, whether it is on the positive side, on the negative side, or on the hyperplane, then we learn much more than just whether there exists one that sums to 0. We learn the sign of the sum of each and every triplet. So this is very simple, and this is essentially was the most complicated step in the reduction from the active learning to this problem in our solution. Yes, and yeah, I think I will finish now, and I will let Shachar take over.
Yeah, thank you very much for the beautiful talk. I can show you now that I took many notes. It was very clear and very understandable. So we even have, I think, time for one short question, if anyone wants to ask now.
Hey, I'll ask a short question then.
Okay.
So, Shay, can you again explain this hyperplane on this slide? So you take the input vector, and what hyperplane do you mean here?
Yeah, so the hyperplane is all the points x that have inner product 0 with the input vector. The input vector is a normal. You think of it as a normal to the hyperplane, which separates the.
And this input, so this input, so you get some input, so some x as an input vector. You're saying, okay.
Yeah, so in the three-sum problem, you get an input vector, which is just a list of n numbers. and you need to determine whether the xi plus x
Okay. I get it.
zero.
I get it.
The input is a normal to a hyperplane, and then you just observe that xi plus xj plus xj plus xk sum to 0 if and only if the inner product, it's a complicated way to say it, the inner product of x and the corresponding binary vector is 0.
Yeah. Okay. I just try to understand what's the vector in this three-sum problem, but now now it's clear. Thanks.
Okay. So thank you very much again.